Hello and Assalamualaikum. Today we want to present our operating system group project on synchronization using Semaphore, bank counter queue management. Alright, now we move on to the first part, which is introduction. Modern systems require safe and efficient resource sharing across multiple threads or processes. Without synchronization, issues like race conditions, data conflicts, or deadlocks may arise. This project simulates a bank queue system to demonstrate Semaphore-based synchronization in action. Each customer is a separate thread, and each bank counter represents a shared resource. A custom Semaphore using wait and signal operations manages access to these counters. Customers arrive at varying intervals and are queued if all counters are occupied, just like in real-life banking. The simulation mirrors how operating system handle concurrent access to limited resources. Ultimately, the project bridges theoretical concepts of process synchronization with a real-world scenario for practical understanding.
So now we go to problem statement. So the first one, people need efficient resource sharing. Modern systems must manage limited resource to avoid problems like data inconsistency, deadlocks, or race conditions. Challenge in managing concurrent process. To ensure multiple threads can access limited resource without causing overlaps or unfair delays. For the third one, solution using Semaphore for synchronization. We can help control access to counters using wait and signal functions so systems stay stable. The last one is real-world example, bank counters. Like customers sharing counters in a bank, this simulation shows how threads can be managed efficiently under limited resources.
Next part is about related works to our project. So some of the related works to Semaphore that can be seen in real-world scenarios is the first one is producer-consumer problem. And this is a classic concurrency issue where we have producer and consumer. The producer will add items to a shared buffer and the consumers will remove them. And the function of Semaphore in here is to manage access and checks whether the buffer is full or empty and limits logs to prevent race conditions. The second problem is a reader-writer problem. And this problem deals with shared data access where multiple readers can read simultaneously but only one writer can modify at a time. Semaphore is to control the access. For example, value more than 1 allows multiple readers and value equals to 1 ensures explicit writing which only one writer can modify at a time. The next problem is print queue management, which is a real-world case where multiple print jobs share a single printer and Semaphore will handle the access, which means that only one process acquires the log to print, and one at this time, the log is released, making the printer available for the next job.
So for our methodology, we simulate a real bank queue system using Python. So our aim is to demonstrate how custom semaphores manage access to limited service counter. Next is our conceptual framework. Thread uses wait function to acquire a counter. So if no counters are available, it will block the threads. When service ends, signal function release the counter for next waiting thread proceeds. So we build our custom semaphore design using trading.condition. We maintain a counter self.value to track available counters. Wait function will check and block threads, and signal function will increment counters and notify waiting threads. This fully replicates classic P function and V function operation from operating system theory. Next is our requirements analysis. For non-functional requirement, we aim for a clean, simple, and readable code. We avoid complex libraries and stuck to basic Python modules. For functional requirements, we simulate a bank queue system where multiple customers request access to limited customers. So we ensure that customers get detected, wait if needed, and are served one by one at available counters. The system limits how many customers can serve at once using our custom semaphore. Next is technology and tools. We choose Python because it's readable and handles multi-threading well. For our outcome, we set clear rules, simulation rules, and system constraint. We create a strong foundation before implementation.
The table of system requirements, we have specified all of the components that we have used, like our programming language, the IDE used, libraries, platform, processor, memory, and also the output mode. Our research focus is where we exploit the Python threading to simulate the concurrent customer threads. As you can see here, the libraries that we use are threading, time, random, and date time. And we also designed a custom semaphore using the wait and signal operations. And our project is modeled after the real bank queues, where a few counters will serve many arriving customers. The insights gained from our project is we learned how to define how threads should behave, when to block, and how to ensure only one customers are allowed to serve at one time. The next part is about tools and communication. So as you can see here, we have two tables. The first table is development tools used, which are Visual Studio Code for our primary IDE, and then we have Python as our programming language, and we also use Programmase or Online GDB for the alternative platform for a quick online testing. And as for the communication and coordination platforms used, the first platform that we used is WhatsApp for our daily communication. The second one is Google Docs for collaborative writing among team members. The third one is Google Meet for virtual meetings, and the last one is face-to-face meeting to ensure that we can have in-depth planning of our project. So all of these tools were chosen based on our familiarity with the tools, the ease of access, and also the effectiveness in supporting both remote and in-person collaboration.
Alright, now we move on to the next part, which is prototyping. Simulation developed to reflect a realistic bank queue system that applies the principle of process synchronization. Custom-built Semaphore was implemented to control concurrent access by multiple customer threads to a limited number of service counters. User inputs configurable parameters is number of customers, number of service counters, service time range, and time gap between customer arrivals. Then, each customer is per thread receiving unique ticket number and randomized banking service like deposit, withdrawal, and others. Semaphore controlled access using wait and signal operations. Activities are logged with timestamps during ticket issued, waiting, and service started and completed. To summarize, this prototype demonstrates mutual execution, controlled thread access, and fair scheduling. Okay, next is testing and validation. The simulation evaluated under multiple real-world light test scenarios. This simulation is conducted to validate concurrency control, which is no counter exceeded capacity, fairness, no starvation, and all threads proceeded. Then smooth performance, handled low and high contention smoothly, and last but not least, output verification. We check the timestamp logs and confirm everything behaves as expected. Here, as you can see, there is test case summary table. We have 3 test cases, which is standard load, high contention, and no blocking. For standard load, we have 10 customers, 3 counters with service duration of 6 to 8 seconds and arrival gap of 2 seconds. For high contention, 8 customers and only 1 counters with service duration of 4 to 6 seconds and arrival gap of 1.5 seconds. And for no blocking, only 3 customers with 5 counters, service duration of 3 to 5 seconds and arrival gap of 2 seconds. For standard load, observed behavior, first 3 threads served immediately and rest queued. For high contention, only 1 thread active and others are blocked due to number of counters is 1. For no blocking, all threads serve instantly and no delay because the number of customers is only 3 with 5 counters.
For design and implementation, this section presents the overall structure and development approach for the bank queue simulation. It is divided into 2 main parts, which are the conceptual design of the system and the implementation details. Both aim to demonstrate synchronization using a custom semaphore in a controlled multi-threaded environment. So the first one is system overview. The bank queue simulation is designed to replicate the behavior of real-world customer service environment, where multiple clients seek service from a limited number of counters. The core objective is to illustrate how trades represented by customers can be synchronized using a custom-built semaphore to ensure orderly access to shared resources. Each customer is modeled as a separate trade, while the bank counters are treated as finite shared resources. A custom semaphore is responsible for managing access to these counters using wait and signal operations, which allow or delay customer service depending on counter availability. Next is design objective. So we have 6 objectives, which is to simulate process synchronization through the implementation of a classical semaphore mechanism, to model realistic queue behavior in a banking environment, to ensure safe, fair, and deterministic trade execution while avoiding common concurrency issues, and then to provide clear visibility of trade states, including waiting, serving, and completion stages, and then to implement a custom synchronization primitive as an alternative to built-in constructs. And the last one is to explore the impact of trade arrival patterns on system behavior and performance. So next is component architecture. We have 5 component architecture. The first one is trade model, which is customer as process. Each customer is represented as a separate trade arriving at random intervals to simulate real-world bank traffic and concurrent processing. Next one is shared resources as bank counters. Bank counters are controlled by a custom semaphore set to 3, limiting access to only 3 customers at a time. Others must wait until a counter is free. Next one is synchronization control, which is custom semaphore. A custom semaphore manages access using an internal counter and condition variables. Trades wait if counters are full and proceed when signaled, ensuring safe and orderly access. For the fourth, queue behavior simulation. Trades that cannot access a counter are blocked until notified. This simulates a fair first come first serve queue like in real banks. For the last one is ticketing and service assignment. Each customer gets a unique ticket, example given A101, and is randomly assigned a service like deposit or loan inquiry, mimicking a real bank operations. The next one is interaction flow. So the simulation starts by asking the user to input number of customers, number of counters, service duration range, arrival and arrival intervals. These inputs control the simulation settings, which each customer trade. For the first step is request a counter using wait, and then if available, it enters the critical section, and then it finishes and calls signal to release the counter. And if no counters are available, the trade is blocked using a condition variable. It waits until notified and then retries wait. So the custom semaphore handles all synchronization, preventing race conditions and enforcing limits on counter access. Ticket numbers and varied service systems add realism and fairness similar to actual bank system.
Next is our programming environment. Our simulation was built in Python using only core modules, such as trading for creating and managing concurrent customer threads. Random is added to introduce variability in service duration and randomly assign service types to customers. Time is added to simulate realistic time delays between customer arrivals and during service execution. And then date time is for providing us with timestamp blocks for clear tracking. Next is implementation. A wait function will check if the resource counter is available. If not, the trade blocks and wait. A signal function releases the resource and notifies any waiting threads. Self.value will track the number of available counters. Wait function will block the thread if no counter is available. And then signal function will increment the counter and notifies one waiting thread. The trading.condition function ensures more mutual execution and coordinated trade access. Next is user input handling. To make simulation adaptable, we prompt the users to enter total number of customers, number of available counters, range of service times, and interval between customers' arrivals. Next is randomization of behavior. To simulate a more realistic banking environment, we added these elements: ticket numbers for each trade receive a unique ticket, service type like deposit, withdrawal, and loan inquiry, and then service duration, a random value within the user-defined range.
So the next part of our implementation is the customer thread function. So as you can see from our code snippets, each thread will log the ticket number and will be assigned a service type upon their arrival. So the wait function here is used to attempt to acquire a counter, and if it's unavailable, the thread will enter a waiting state until it is notified. And the sleep function here simulates a service duration using a randomized time interval between minimum service and maximum service, which are set by the user input. And then we also assign a counter number, which is calculated dynamically based on the number of counters that is entered by the user. And once the service is completed, the signal function is called to release the counter and wake any waiting threads from here. So the next one is thread management and execution. So after all threads are created and started, the program ensures completion of all customer interactions using the join method here. So T.start method initiates that each customer thread sequentially with the user-defined delay between thread launches. And then the T.join method ensures that main program waits for all threads to finish execution before completing the simulation. So this use of threads simulates a real world queue environment where multiple customers may arrive in overlapping intervals, but they are served based on the resource availability. The last part of our implementation is logging and output behavior. As for the logging, as you can see here, we utilize the datetime library in Python because each significant event in the thread's journey, such as the ticket assignment, the waiting in queue, service start, and service completion, all of these events are recorded with an accurate timestamp using the datetime module. And for the output behavior, by analyzing all of the outputs here, as you can see, like customer received ticket, customer is being served the counter, we can confirm the proper sequencing of the thread execution, the accurate handling of the block threads, and also the absence of race conditions or deadlocks.
Alright, now we move on to the next part, which is results and discussion. The first one is overview of testing scenarios. So multiple test scenarios were designed using various user-defined inputs, which is number of customers, number of available counters, range of service durations, and arrival intervals between customers. The goal is to observe how the custom semaphore manages concurrent access control, thread blocking and wake-up behavior, and fairness and proper synchronization. For test scenarios, we have 3 scenarios, which is standard load scenario, moderate number of customers with several counters to verify normal synchronization behavior, then high contagion scenario, few counters with many customers to evaluate blocking and queuing efficiency, and last but not least, no blocking scenario, more counters than customers, confirming immediate access without any thread suspension. Alright, now we move on to simulation output and case analysis. So for this, figure 6.1 illustrates the buffer model used in the BenQ simulation. Customer threads request access to available counters controlled by a semaphore initialized to n, which is the number of counters. Threads call wait to enter service, which is critical section. After service, they call signal to release the counter. The green blocks means occupied counters, while white blocks is mean available counters. This model ensures orderly access, no counter of use, and no race conditions. Okay, now we move on to the first scenario, which is standard load scenario. For test case configuration, we have 10 customers, 3 counters with service duration 6 to 8 seconds, and arrival gap between customers with 2 seconds. For key observations, first 3 customers access counters instantly, then remaining customers waited their turn in the queue. Semaphores wait and signal operations control the access, ensured only 3 threads only in the critical section at a time. This simulated steady throughput and fair access under moderate load. Then, this is the simulation activity timeline for standard load scenario. As you can see here, the service started for 3 first customers, then the rest is waiting in queue, waiting for the first 3 customers complete their services. Then they will enter the service, which is the critical section. This is continued until all the customers complete their service. To conclude, the system operated smoothly under standard load, queue formation, and serving order aligned with expected behavior. The semaphore mechanism properly enforced mutual exclusion, and no starvation or race conditions were observed.
Great. So for the second scenario is high contention. For the test case configuration, number of customers is 8, number of counters is 1, service duration is 4 to 6 seconds, and arrival gap is 1.5 seconds. So the key observation from this scenario is first customer accessed the counter without delay, and then remaining trades were blocked and entered a wait queue, and then wait operation enforced orderly blocking for all others. Signal operation resumed trades sequentially as the counter became free, and then confirmed proper blocking, fairness, and deadlock free operation. So this is the simulation activity timeline. You can see here. And then there's also the activity timeline. And then the semaphore enforced strict access control under pressure. So only one track was served at a time, and all others waited in order. This confirmed that the simulation effectively handled high contention, maintained fairness, and prevented any race conditions. And then we have no blocking scenario. For the test case configuration, number of customers is 3, number of counters is 5, service duration is 3 to 5 seconds, and arrival gap is 2 seconds. So the key observations for this scenario is number of counters exceeded number of customers. All trades access the critical section without delay. No use of wait operation since no trade needed to block. So every customer trade proceeded directly to service and then confirmed optimal responsiveness with no resource contention. So this is the simulation activity timeline. The semaphore demonstrated adaptability in a low load environment with more counters than customers. No trades were forced to wait, and system throughput was maximized. This confirmed that the custom synchronization logic correctly avoided unnecessary blocking and allowed efficient utilization of resources. So for comparative evaluation and insights, for the first one is synchronization effectiveness. So the key observations for the first scenario, which is standard load, the system handled a moderate number of customers effectively. The first few trades accessed counters immediately, while others waited and were served in order. Smooth transitions between waiting and service stages enabled by the custom signal operation confirmed that synchronization was functioning as expected. And then for high contention scenario, with only one counter available, trades were correctly blocked using the wait operation function. As counters became free, blocked trades resumed service in the correct order. This ensured strict access control, avoided overlaps, and demonstrated fairness in trade handling. And then for the last scenario is no blocking, which is no blocking. All trades entered the critical section without delay as more counters were available than customers. No trade had to wait, showing that the semaphore logic did not unnecessarily enforce blocking. This verified the system's ability to adapt under low load conditions while maintaining efficiency.
Next part of our discussion for the comparative evaluation and insights is the performance comparison. As you can see from the table, we have compared all the performance for each scenario, the standard load, high contention, and no blocking. So as for the standard load scenario, we used 10 customers with 3 counters. As you can see here, the resource utilization for this scenario is moderate and the blocking is also moderate. For high contention, we test only one available counter for 8 customers. So this scenario is the most threats being blocked by upon arrival. So the resource utilization is high and the blocking behavior is also high. As for the no blocking scenario, only 3 customers were served using 5 available counters. So there are no blocking behavior and there are very low resource utilization in this scenario. We have also provided charts to compare the performances. So the first one, we compared the average wait time across scenarios. So from this chart, as you can see, the highest average waiting time occurred in high contention. This is because there are limited number of counters which force most customers to wait before being served, resulting in the highest average wait time. And in standard scenario, it's all moderate delays, while in no blocking, there are no recorded waiting time, which highlights the semaphore's ability to avoid unnecessary queuing when the resources is sufficient. The next part is where we compare the counter utilization by scenario. So this chart illustrates how the counter usage varied across the task cases. So in the high contention scenario, we only have a single counter which is fully utilized and it shows maximum resource pressure. And in standard scenario, it demonstrates a good usage across multiple counters. And in no blocking, no more counters were available than needed, so it results in idle time. So the last chart that we have made to compare the performances for each scenario is the blocking frequency by scenario. So as you can see, the blocking is the most frequent in high contention scenario due to the presence of only a single available counter. In standard scenario, the moderate blocking were shown because there were blockings, but it was resolved promptly due to the balanced arrival intervals between the threads and also the sufficient concurrency support. And in no blocking scenario, it exhibits zero blocking. It confirms that our semaphore logic adapted effectively to the resource abundance, which allows smooth thread execution without any unnecessary delays.
Lastly, summary of findings. Firstly, mutual exclusion is maintained. Semaphore is constantly restricted access to match available counters, so this prevents resource overlap. And then customers were served in order with waiting threads resumed predictably. So next is race condition avoidance. All shared resource interactions were synchronized, so no threads access counters concurrently. And then we have adaptive blocking behavior. Threads waited only when needed. So if a counter was free, the customer don't have to wait. And then adaptability across scenarios handled moderate, high, and no contention cases efficiently. It demonstrates robust and reliable semaphore behavior.
Moving to the next part, which is future works. So there are 4 key improvements that we identified. Firstly, priority-based queuing. We plan to enhance the current first come first served logic by serving customers based on priority levels. For example, VIP, urgent, and regular, or type of service. Secondly, service-based prioritization. We plan to modify wait to select the highest priority customer and signal to notify the next eligible trade based on both priority and counter availability. Third, we aim to simulate multi-step transaction, which is to reflect the realistic banking operations that require multiple sequential steps. Finally, multiple critical sections. We will introduce different semaphores to manage each service stage, allowing customer trades to pass through several critical sections in order.
The first one, the importance of synchronization. We discovered how vital synchronization is in managing shared and limited resources in real-world systems. And then we found the benefits of Semaphore. We learned additional benefits of Semaphores, which is mutual exclusion, no busy waiting, and efficient resource sharing. And for the third is avoiding race condition, which is showing that without proper control, like Semaphores, multiple threads can interfere and cause data inconsistency. And for the last one, which is FCFS, limitation and future improvement. We recognize FCFS not very realistic, and then introduce priority levels, BIP, urgent, regular, to improve fairness and accuracy. And that's all from us. Thank you.